Picture in your mind a time 2 million years in the past when an extraordinary species inhabited our planet. These weren't people like you and me, but rather a species destined to persist for nearly 20 times longer than modern humans have existed. Their narrative goes beyond mere fascination. It stands as the greatest story of human achievement and endurance ever told. This is Homo erectus, literally speaking, the most accomplished human species in all of history. If you're listening to this to help you drift off to sleep, that's exactly why I create these videos. So consider subscribing and let me know your location and the time you're listening. I read the comments and it's like Sydney at sunrise, Seattle at bedtime, all happening simultaneously. Before we dive deep into their world, let's take a moment to truly appreciate the scale of what we're about to explore. When we talk about 2 million years, we're discussing a time span that's nearly impossible for the human mind to fully grasp. Think about it this way. If you were to count to 2 million, spending just 1 second on each number, it would take you over 23 days of continuous counting without sleep. Now imagine each of those numbers representing not a second, but an entire year of existence. That's the magnitude of Homo erectus's reign on this planet. During their time on Earth, entire mountain ranges rose and eroded. Ice ages came and went repeatedly, and the very face of our planet transformed in ways both subtle and dramatic. Continents shifted, coastlines changed, and ecosystems evolved and disappeared. Through all of this, Homo erectus adapted, survived, and thrived. What sets their journey apart from all others? They existed long enough to inhabit this world for an incredible span of 2 million years. 2 million. That's a duration so enormous that our minds have difficulty grasping its magnitude. To put this in context, our own species, Homo sapiens, has been around for merely 300,000 years, making us essentially the newcomers on the evolutionary timeline. Meanwhile, Homo erectus, these extraordinary ancient humans, ruled the landscapes of Earth across 3 continents for a stretch of time that renders our entire history insignificant by comparison. Think about all of recorded human history: the pyramids of Egypt, the Roman Empire, the Renaissance, the Industrial Revolution, the digital age. All of human civilization as we know it spans only about 10,000 years. That's just half of 1% of the time Homo erectus walked this earth. Our entire species, from the first anatomically modern humans to every person alive today, represents only 15% of Homo erectus's incredible tenure. If we were to compress all of Homo erectus's existence into a single 24-hour day, our species would have only appeared in the last hour and 48 minutes. All of recorded human history would occupy just the final 7 seconds. This perspective is absolutely staggering when you really let it sink in. I'm going to guide you through an expedition across time to uncover how these ancient people existed, their physical appearance, their cognitive abilities, and the reasons they're so vital to comprehending what being human truly means. You'll learn why countless scientists regard Homo erectus as the first genuine humans in our evolutionary journey, a species that resembled us more closely than any creature that preceded them. Their appearance mirrored ours, their movement patterns matched ours, and they probably communicated in manners remarkably similar to our own. And here's something that will blow your mind. They weren't simply unsophisticated cavemen wandering aimlessly with rudimentary implements. New findings have uncovered their remarkably developed abilities, from manufacturing complex stone tools to constructing protective structures, and even demonstrating signs of tending to their sick and elderly. The archaeological evidence paints a picture of a species that was innovative, adaptive, and remarkably resilient. They faced challenges that would have destroyed lesser species ice ages that turned vast regions into frozen wastelands, droughts that dried up rivers and lakes, volcanic eruptions that blanketed the landscape in ash predators that would make modern lions and bears look tame by comparison. Yet through all of this, Homo erectus not only survived, but thrived, spreading across 3 continents and adapting to environments ranging from tropical jungles to temperate woodlands to high mountain plateaus. Their capacity for navigating 2 million years of shifting climates and dangerous carnivores genuinely established the groundwork for our presence here today. Every time you use fire to cook food, every time you craft a tool to solve a problem, every time you care for someone who is sick or injured, you're echoing behaviors that Homo erectus pioneered almost 2 million years ago. Let's frame their remarkable story properly. Homo erectus made their first appearance approximately 2 million years ago and persisted until as recently as 100,000 years in the past. That's correct. The final groups of Homo erectus were still alive on this planet at the very same time our own species was starting to migrate across continents. This temporal overlap is one of the most fascinating aspects of human evolutionary history. For thousands of years, possibly even tens of thousands of years, multiple human species coexisted on this planet. It wasn't just Homo erectus and Homo sapiens either. Neanderthals were thriving in Europe and Western Asia. Denisovans inhabited parts of Asia. The diminutive Homo floresiensis, sometimes called hobbits, lived on the island of Flores in Indonesia. For a brief moment in geological time, Earth was home to a diverse array of human species, each with their own unique adaptations and capabilities. The most recent Homo erectus remains originate from Ngandong on Java Island in Indonesia, where scientists unearthed a dozen skull caps, along with 2 leg bones that date to roughly 108 to 117,000 years before present. The site itself is remarkable. The bones were found in a river terrace deposit, suggesting they may have been washed together by ancient floods or deliberately placed there by other hominins. The skull caps show interesting patterns of damage, some appearing to have been deliberately opened at the base, which has led to speculation about possible cannibalistic practices or ritual treatment of the dead. But we'll explore those darker possibilities later in our journey. This obviously brings up an intriguing question. Could Homo erectus and Homo sapiens have crossed paths? Did our immediate ancestors ever come face to face with these ancient people who had reigned over the world for such an extended period before we arrived? It's an enticing prospect that scientists have been exploring for many years. The idea of such a meeting captures the imagination. What would it have been like for these 2 species to encounter each other? Would they have recognized each other as kin, or would they have seen each other as competitors, or perhaps even as prey? Would they have been able to communicate in any meaningful way? Could they have interbred, sharing genetic material that might persist in modern human populations? These questions drive ongoing research and fuel countless debates among paleoanthropologists. We understand that Homo sapiens departed from Africa, heading toward Europe and Asia around 90,000 years ago, though that chronology continues to be revised with recent discoveries. Every few years, it seems, archaeologists unearth new evidence that pushes back the timeline of human migration. A Homo sapiens fossil discovered at Mislia Cave, located in Israel, dates to somewhere between 177,000 and 194,000 years ago, indicating we left Africa significantly earlier than scientists previously believed. This particular fossil, a partial upper jaw with several teeth still attached, has revolutionized our understanding of human dispersal patterns. The teeth show wear patterns consistent with a diet of both plant and animal materials, and the robust jaw structure suggests these early migrants were well adapted to processing tough foods. But here's the interesting part. The most ancient proof of Homo sapiens' presence on Java, where Homo erectus held on the longest, dates to somewhere between 60 and 70,000 years ago. So regrettably, it appears Homo erectus didn't persist long enough on Java to encounter modern people. By the time our species arrived on those tropical islands, Homo erectus had already vanished, leaving behind only their bones and tools as silent testimony to their long occupation. And truthfully, no fossil evidence anywhere across the globe definitively demonstrates direct meetings between Erectus and modern humans. No cave paintings depicting encounters between the two species, no mixed campsites where both species left their distinctive tools, no skeletal remains showing evidence of conflict or cooperation between the groups. The absence of evidence, however, doesn't necessarily mean evidence of absence. The fossil record is notoriously incomplete. Only a tiny fraction of all organisms that have ever lived become fossilized, and only a tiny fraction of those fossils are ever discovered by paleontologists. It's entirely possible that Homo erectus and Homo sapiens did meet, perhaps many times, but those encounters simply didn't leave traces that have survived the passage of time or haven't yet been discovered. Archaeological sites are being excavated constantly, and new discoveries are made every year. Perhaps someday a researcher will uncover definitive proof of such an encounter. But hold on, there's a surprising development in this narrative coming from an extremely improbable place. Head lice. Yes, you understood that correctly. These tiny parasites that have plagued humanity throughout our existence may hold clues to ancient encounters between human species. Based on studies published in the Public Library of Science Biology, human head lice actually originate from two distinct lineages that separated roughly 1.18 million years ago, an era when Homo erectus was flourishing but well before modern Homo sapiens came into being. Now, you might be wondering why scientists would study head lice to understand human evolution. The answer is actually quite fascinating. Parasites evolve alongside their hosts, and the evolutionary history of lice can tell us a great deal about the evolutionary history of the species they infest. When a host species splits into two separate populations that don't interbreed, their parasites also split into separate populations. Over time, these parasite populations evolve independently, becoming genetically distinct from each other. By examining the genetic differences between modern lice populations and calculating how long it would take for those differences to accumulate, scientists can estimate when the host populations separated. One lineage of these parasites is distributed worldwide and went through a population bottleneck approximately 100,000 years ago, corresponding with the spread of modern humans. A population bottleneck occurs when a species undergoes a dramatic reduction in population size, usually due to some environmental catastrophe or other major event. When this happens, genetic diversity decreases dramatically because only a small subset of the original population's genes survive to be passed on to future generations. The lice associated with modern humans show evidence of such a bottleneck, which makes sense given that our own species also went through a population bottleneck around the same time. But the second lineage, discovered only in the Americas, has stayed isolated for the complete 1.18 million years. This is where things get really interesting. These lice are found exclusively in Native American populations, and their genetic distinctiveness suggests they've been evolving separately from other human lice for well over 1 million years. How could this be? Modern humans only reached the Americas about 15,000 to 20,000 years ago, far too recently to account for such ancient genetic divergence in their parasites. The separation between these lineage groups matches early hominid divergences, implying they developed alongside separate human species. If these parasites genuinely evolved with Homo erectus 1.18 million years ago, then the reality that modern humans carry them indicates a direct transmission must have occurred, which would necessitate physical interaction between Homo erectus and early Homo sapiens. But because no fossil evidence confirms direct meetings, scientists stay doubtful. The lice evidence offers one of numerous intriguing enigmas surrounding these ancient people that investigators are still attempting to unravel. Some researchers have proposed alternative explanations. Perhaps the lice jumped from Homo erectus to an intermediate species like Homo heidelbergensis or denisovans, and then eventually made their way to modern humans through that intermediary. Or perhaps the genetic dating methods aren't as accurate as we think, and the split between lice lineages occurred more recently than the genetic data suggests. The initial Homo erectus remains were found in 1891 by a Dutch researcher named Eugene Dubois. Following years of exploring Indonesia for what researchers of that era termed the missing connection between apes and humans, Dubois excavated a well-maintained skull cap at Trenil on the Solo River on Java Island. The specimen possessed prominent brow ridges, a sloping forehead, and an angled back of the skull, characteristics that Dubois asserted represented the evolutionary bridge between apes and modern people. Fellow scientists at first rejected his analysis, but Dubois was ultimately proven right when comparable Homo erectus remains were unearthed in China throughout the 1920s and 30s. These findings validated that this was truly a geographically extensive human species that had occupied enormous territories across Africa, Asia, and Europe. One of the most noteworthy features about Homo erectus was their evolutionary progression toward increased brain capacity. Early representatives of the lineage possessed a cranial volume of 600 to 800 cubic centimeters, like the Dmanisi skull, designated D2700. Discovered at the Dmanisi location in Georgia, whose measurements were nearer to earlier Australopithecines than to later humans. This site in Georgia, by the way, has yielded some of the most complete and best preserved early Homo erectus fossils ever found, providing unprecedented insights into what these early humans looked like and how they lived. The Dmanisi fossils are particularly important because they represent some of the earliest evidence of Homo erectus outside of Africa, dating to approximately 1.8 million years ago. What makes these fossils even more remarkable is that they show significant variation among individuals, suggesting that what we call Homo erectus may have actually encompassed a considerable range of physical forms. Some researchers have even proposed that what we currently classify as several different species, including Homo habilis, Homo rudolfensis, and Homo erectus, might actually all be variations within a single highly variable species. This idea remains controversial, but the Dmanisi fossils have certainly forced scientists to reconsider how we categorize early human species. But across time, as they encountered new ecological obstacles and adjusted to varied habitats, their evolution witnessed substantial advancement in brain capacity and intricacy. Middle Pleistocene, Homo erectus skulls from Africa, Asia, and Europe display volumes reaching 1,230 cubic centimeters, attaining the identical capacity as Albert Einstein's brain. This progression didn't happen overnight. It took hundreds of thousands of years for Homo erectus brains to evolve from the smaller early forms to the larger later ones. And this evolution wasn't uniform across all populations. Some groups of Homo erectus developed larger brains than others, likely in response to different environmental challenges and opportunities. This is remarkable because large, intricate brains can handle and retain significantly more data, enabling more advanced behaviors and modifications. But large brains also come with significant costs. The human brain, despite making up only about 2% of our body weight, consumes roughly 20% of our energy. For Homo erectus, supporting an increasingly large and energy-hungry brain would have required significant changes in diet and behavior. They would have needed to consume more calories, particularly more protein and fat, which likely drove their increasing reliance on hunting and meat consumption. They also would have needed to develop more efficient ways of processing food, which brings us to the importance of fire and cooking, topics we'll explore in detail later. The enlargement of the Homo erectus brain also had implications for social behavior. Larger brains generally correlate with more complex social structures in primates. As Homo erectus brains grew, they likely became capable of more sophisticated social interactions, better able to maintain relationships with larger numbers of individuals, more skilled at cooperating in hunts and other group activities, and perhaps even developing the early foundations of culture and tradition. Some researchers have proposed that it was during the time of Homo erectus that our ancestors crossed a cognitive threshold that separated them fundamentally from earlier hominins and from other primates. A threshold that put them on the path toward the even more complex cognitive abilities that would characterize later human species. Homo erectus possessed a unique appearance that distinguished them from both previous species and from us modern humans. They were the first humans to possess a comparatively flat face and a projecting nose, characteristics believed to have assisted them in retaining moisture when inhaling dry air in the diverse environments they occupied. But different from modern humans, they also possessed a flat, sturdy, low skull with massive brow ridges. These substantial brow ridges have captivated scientists. What function did they fulfill? In 2004, anthropologists Noel Boaz and Russell Siochon proposed something unexpected. They theorized these characteristics resulted from a behavioral practice where Homo erectus would battle each other with fists, rocks, or wooden weapons to resolve conflicts or vie for reproductive partners. The architecture of their skull appears strikingly well suited for withstanding severe impacts. The heavy brow ridge shields the eyes and extends into a bar protecting the ears, linking all the way to the rear of the skull. This means impacts to any of these areas could be successfully distributed across the skull. Fascinatingly, numerous fossil skull caps display severe fractures that would typically be incapacitating, yet they also display evidence of recovery, indicating these individuals lived through potentially fatal head injuries. Anthropologist Peter Brown proposed a comparable explanation for the peculiar thickening observed in modern Australian Aboriginal skulls, a consequence of a ceremony practiced in central and southeast Australian communities where opponents would hit each other with clubs until unconsciousness. So these substantial brow ridges may have served as both a social indicator, displaying strength and superiority, and a functional modification reinforcing the skull against blows. As humans developed toward our modern appearance, we slowly lost these marked characteristics as social interaction became more significant, permitting us to interpret nuanced emotions in one another's faces. Our entire facial architecture transformed to emphasize interaction over physical defense. Their jaws were also considerably more sturdy than ours, broad and dense without a protruding chin. In terms of teeth, Homo erectus possessed the thinnest enamel among all early human species. While enamel protects teeth from fracturing when consuming hard foods, it also makes it more difficult to cut through fibrous foods. Their jawbones were considerably thicker than those in modern humans and living apes, which would have permitted their jaws to withstand twisting during biting or masticating, potentially allowing for exceptionally powerful forces while eating. Interestingly, their teeth display a greater frequency of pits in their premolars and molars relative to earlier species like Homo habilis. This suggests a diet abundant in brittle foods, possibly influenced by their sophisticated tool use, which permitted them to prepare a broader array of foods than their ancestors. Like modern humans, Homo erectus differed extensively in stature, spanning from 4 feet 9 inches to 6 feet 1 inch in height and 40 to 68 kilograms in weight. This variation was probably due to regional distinctions in climate, death rates, and food availability among primates. This degree of phenotypic flexibility, the capacity to display pronounced physical reactions to environmental pressures, is genuinely very uncommon and is only exhibited in modern humans and Homo erectus. Homo erectus displayed sexual dimorphism, observable distinctions in stature, and occasionally other physical traits between males and females. Generally speaking, male Homo erectus individuals were inclined to be bigger and more powerfully built than females. This sexual dimorphism is deduced from fossil evidence, encompassing variations in skeletal dimensions and structure. Over 971,500-year-old footprints created by no fewer than 20 separate individuals from near Eret, Kenya, reveal that Homo erectus was more sexually dimorphic than modern Homo sapiens, though less so than highly dimorphic apes such as gorillas and vanished species like Australopithecus, Apricus, and Paranthropus robustus. These footprints provide a distinctive glimpse into a significant transitional phase in hominid social dynamics, pointing to a social arrangement somewhere between the extreme male-controlled groups of great apes and the more balanced structures of modern humans. These identical footprints also disclose something extraordinary about how Homo erectus traveled. They reveal that Homo erectus was the first species in the human lineage to possess a modern human gait. The footprints and skeletal evidence indicate they possessed approximately the same limb configurations and ratios as modern humans, suggesting human-like movement that would have been significantly more effective for long-distance travel than the gait of earlier human species. Homo erectus were also the first in our lineage to have a human-like shoulder, indicating an aptitude for high-velocity throwing. This modification would have been a substantial evolutionary benefit, permitting them to successfully launch rocks, wooden spears, or other projectiles, aiding the hunting of large game for precious, calorie-dense meat. This stands in dramatic opposition to their early hominid ancestors such as Homo habilis, who still possessed chimpanzee-like shoulders, poorly adapted for precise object throwing. When we examine the fossil record, it becomes evident that Homo erectus represented a substantial transformation in human evolution. The appearance of a species that, while still separate from us in numerous ways, possessed a collection of physical and cognitive modifications that would characterize the human lineage for millions of years to follow. These weren't merely somewhat enhanced versions of earlier hominids. They were a transformative new kind of human, outfitted with bodies designed for stamina, accuracy, and flexibility, but their physical modifications were just the start of what made Homo erectus so exceptionally accomplished. In our following segment, we'll investigate one of their most characteristic and astonishing features, their surprisingly bare bodies, and learn how this seemingly straightforward modification may have performed a vital role in their evolutionary triumph, establishing the foundation for the advancement of the large brains that would ultimately characterize our own species. We'll also examine their extraordinary tool innovation, hunting approaches, and social organizations, all components that assisted them in becoming the most accomplished human species in evolutionary history. Remain with me as we proceed with this amazing expedition through time to comprehend our most accomplished ancient family members. As primates and mammals, we humans have a unique characteristic that distinguishes us from the majority of our evolutionary relatives' comparatively hairless skin. While aquatic mammals like whales and dolphins, together with elephants, possess this trait, most primates and mammals are usually covered with a furry layer. So when did humans shed their body hair, and for what reason? It happens that Homo erectus was the first representative of the genus Homo to develop this hairless state, with investigations indicating this modification appeared no less than 1.2 million years ago. But to comprehend why humans possess considerably less body hair than other primates, we need to acknowledge that mammalian body hair isn't simply a cosmetic characteristic. It shields the skin from injuries, parasites, heat, cold, and ultraviolet radiation. So why would an early human species develop to shed this protective layer? The most broadly acknowledged evolutionary explanation is heat release. When early representatives of the genus Homo relocated from inhabiting shaded forests to the exposed savanna, shedding body hair and acquiring more sweat glands made it simpler for their bodies to cool off during prolonged physical exertion. This environmental change also initiated a substantial alteration in diet, from predominantly vegetarian to progressively hunting-oriented chasing game across the hot savanna, significantly intensified the requirement for efficient body temperature control. And here's where it gets genuinely interesting. Anthropologist and paleobiologist Nina Jablonski suggests that the capacity to release excess body heat through productive sweating actually helped enable the substantial expansion of the brain, the most temperature-vulnerable human organ. So, the disappearance of fur wasn't just about remaining cool. It potentially enabled further modifications, both physical and behavioral, that separated humans from other primates. Some investigators think sexual selection hastened these alterations. By choosing more hairless partners, Homo Erectus may have quickened changes that were at first triggered by natural selection forces. This hairless modification raises another captivating question. What about skin pigmentation? Most mammals possess light skin protected by fur, and biologists think early human forebears started out this way too. But this transformed with Homo erectus. Genetic examination indicates that high activity in the melanocortin 1 receptor gene, which generates dark skin, dates back to Homo erectus roughly 1.2 to 2 million years ago. Dark coloration, specifically melanin, functioned as a natural sun protector, assisting to avoid skin harm and diminish the likelihood of conditions like skin cancer in areas with high sun exposure. Possessing dark skin would have delivered a survival benefit for Homo erectus by providing superior defense against the sun's powerful rays. However, as groups of Homo erectus migrated to higher latitudes with less powerful sunlight, they potentially acquired lighter skin to avoid vitamin D insufficiency. Think about the pattern of modern human movement. The earliest sapiens emerged in Africa under the tropical sun, then traveled into Asia and spread to encompass Europe. Given that Homo erectus had more time to distribute across and adjust to Asia and Europe, it's logical to presume they would have displayed comparable skin tone adaptability to what we observe in modern human populations today. Supporting this hypothesis, a 500 to 300,000-year-old Homo erectus specimen from Turkey was identified with the earliest documented case of tuberculous meningitis, a condition usually worsened in dark-skinned people inhabiting higher latitudes due to vitamin D shortage. This indicates this individual may have possessed darker skin in an environment where lighter skin would have been beneficial, perhaps showing that skin color modification was still developing in these northern Homo erectus populations. Another captivating dimension of Homo erectus biology pertains to brain maturation. A 1.8 million-year-old Homo erectus specimen designated Mojo Sherto, one discovered in Java, who perished at roughly 1 year of age, already possessed 72 to 84% of average adult brain capacity. Contrast this to modern human 1-year-olds, who usually have only attained around 50% of their adult brain capacity. This uncovers something extraordinary. Homo erectus possessed a quicker brain growth pattern more comparable to great apes than to modern humans. This shows that Homo erectus was likely not cognitively equivalent to modern humans, and that our prolonged childhood and extended period of reliance, due to the substantial amount of time necessary for brain development, developed much later in human evolution, perhaps in the modern human and Neanderthal most recent common ancestor. While Homo erectus might not have attained the intellectual abilities of modern humans, they would have still been at the peak of the cognitive ladder on the world during their era. Their bigger brains and sophisticated tools indicate problem-solving capacities and social intricacy far surpassing earlier human species. Some scientists separate between the African erectus, which they designate Homo ergaster, and Asian erectus, which they designate Homo erectus sensu stricto, because of somewhat different traits. For instance, the face of the African individuals is inclined to be taller and less wide across the eye sockets. But it's worth mentioning that modern humans today also display regional differences in physical traits, and we don't get divided into separate species classifications. Many scientists now simply group them together as Homo erectus, which not only makes more sense taxonomically, but also streamlines conversations about their evolutionary past. Speaking of evolution, where did Homo erectus originate from? It's broadly accepted that Homo erectus originated from an earlier species, Homo habilis, an early representative of the genus Homo, who still had ape-like characteristics, including elongated arms and a somewhat protruding face. This shift happened roughly 2 million years ago. However, this simple evolutionary route has been questioned because Homo habilis and Homo erectus remains show they lived simultaneously for no less than 500,000 years. This coincidence proposes either that a particular isolated population of Homo habilis developed into Homo erectus while other Homo habilis populations persisted unaltered, or that Homo erectus might have originated from an early, as yet undiscovered primitive Homo species. It's also intensely disputed where Homo erectus developed as remains dating to around 2 million years ago have been discovered in both Africa and China. A 2011 investigation proposed that it was Homo habilis who first arrived in West Asia from Africa, and that early Homo erectus emerged there before dispersing to East Asia, Southeast Asia, and back into Africa, where they ultimately developed into modern humans. Other investigations have indicated that Homo erectus emerged in Africa, where separate populations ultimately led to the appearance of later hominin species such as Homo heidelbergensis, and ultimately to our own species Homo sapiens. At the start of its time span, around 1.9 million years ago, Homo erectus lived together in East Africa with multiple other early human species, including Homo rudolfensis, Homo habilis, and Paranthropus boisei. Occasionally remains from these separate species have even been discovered at the identical locations, indicating they occupied territories and resources together. At the conclusion of its time span around 100,000 years ago, Homo erectus potentially lived together with Homo floresiensis in Indonesia. Given the time period and geographic location, there's also a good probability they may have encountered with and even crossbred with the enigmatic Denisovans in Southeast Asia. This could potentially clarify the ghost genomes identified in Denisovan remains, which scientists have been able to retrieve from just a pinky bone and 2 molars discovered in Denisova Cave in Siberia. How did Homo erectus hunt and collect food? Persistence hunting has been proposed as a primary approach for meat procurement, thanks to their bipedalism, slender physique, and hairless skin that enabled effective temperature control through perspiring during extended pursuits. Homo erectus could potentially maintain running for up to 5.5 hours without water. This would have provided them a considerable benefit in outrunning prey, establishing them as extremely accomplished hunters. The concept of persistence hunting is fascinating and represents a unique hunting strategy that few predators employ, Unlike the ambush tactics of lions or the burst speed of cheetahs, persistence hunting relies on outlasting the prey. Here's how it would have worked. Homo erectus hunters would identify a target animal, perhaps a kudu or gazelle, and begin pursuing it. The animal would flee, easily outrunning the human hunters at first, but the humans wouldn't give up. They would track the animal, following its footprints and other signs, and every time they caught up to it, they would force it to run again. The key to this strategy lies in thermoregulation. Most mammals cool themselves primarily through panting, which they can only do effectively when they're standing still. Humans, with our exceptional ability to sweat and our lack of fur, can cool ourselves while running. So while the prey animal would overheat after repeated sprints and need to stop to cool down, the human hunters could keep moving, relentlessly pursuing their quarry. After hours of this relentless pursuit, the prey animal would eventually collapse from exhaustion and hypothermia, unable to run any further. At that point, the hunters could dispatch it with relative ease. This hunting strategy would have required remarkable endurance, sophisticated tracking skills, the ability to coordinate with other hunters, and crucially, the mental fortitude to continue pursuing an animal for hours, even when it seemed to be getting away. It's a testament to both the physical and cognitive capabilities of Homo erectus. Some researchers believe that this hunting strategy may have been one of the key selective pressures driving the evolution of larger brains in Homo erectus. Successful persistence hunting requires the ability to track animals over long distances, to predict where they might go, to coordinate with other hunters, and to maintain motivation over extended periods. All of these skills would have favored individuals with enhanced cognitive abilities. Their hunting approaches and prey choices would have relied on the accessible resources in their individual territories and habitats. But Homo erectus is thought to have been a flexible hunter-gatherer, hunting a range of animals for nourishment. Evidence indicates they hunted birds, deer, wild boar, and even elephants. The diversity of prey species in their diet speaks to their adaptability and opportunism. They weren't specialized hunters limited to a particular type of prey. Instead, they could adapt their strategies to whatever animals were available in their environment. In 1988, scientists discovered the remains of an elephant and many dismembered skeletons of giant, now vanished baboons, together with 400 flake tools near Olorgesailie, Kenya, dating from between 790,000 and 992,000 years ago. The Olorgesailie site is actually one of the most important Paleolithic sites in the world, with archaeological deposits spanning nearly 1 million years of human occupation. It's located in the Great Rift Valley of Kenya, an area that has been absolutely crucial for understanding human evolution. The site was first discovered in 1919 and has been excavated extensively since then, revealing layer upon layer of artifacts and fossils that document how human technology and behavior changed over vast stretches of time. Numerous bones possessed clear cut marks, and the animals' limbs were absent. If these animals had truly been hunted rather than scavenged, it would have demanded considerable skill to bring down such formidable creatures, indicating Homo erectus hunted in collaborative groups, which consequently suggests they probably possessed some form of basic language or communication method. The question of whether these elephants were hunted or scavenged has been hotly debated. Elephants are massive, dangerous animals, and killing one with Stone Age technology would have been an enormous undertaking. However, the pattern of cut marks and the absence of carnivore tooth marks on many of the bones suggests that Homo erectus had primary access to these carcasses, meaning they got to them before any carnivores did. This strongly implies hunting rather than scavenging. If Homo erectus really were hunting elephants, how would they have done it? Some researchers have proposed that they might have used fire to drive elephants into swamps or other areas where they would become trapped. Others suggest they might have used spears or heavy rocks to attack the animals, perhaps targeting juveniles or sick individuals rather than healthy adults. Group coordination would have been absolutely essential. A single human, no matter how skilled, couldn't bring down an elephant, but a group working together, communicating effectively and coordinating their actions could potentially succeed. This kind of cooperative hunting would have required social bonds, trust, and the ability to share plans and coordinate actions, all of which imply relatively advanced cognitive and communicative abilities. It can sensibly be assumed that, as with contemporary hunter-gatherers such as the African San Bushmen and Australian Aboriginals, meat from hunting constituted only part of the diet of Homo erectus. Other food sources may have encompassed snakes, birds and their eggs, locusts, scorpions, centipedes, tortoises, rodents, hedgehogs, fish and crustaceans. Even youngsters could have captured many of these, as they still do in Africa's Kalahari Desert today, before being permitted to join older males on more hazardous hunts. This point about children contributing to food gathering is important and often overlooked. In modern hunter-gatherer societies, children aren't simply passive dependents waiting to grow up. They actively contribute to the group's subsistence from a young age. Even very young children can collect insects, dig for tubers, gather fruits and nuts, and catch small animals. As they grow older and more skilled, they gradually take on more challenging tasks, learning through observation and practice. By the time they reach adulthood, they've accumulated years of practical knowledge about their environment and how to extract resources from it. This pattern of childhood learning and contribution was likely present in Homo erectus societies as well. Young Homo erectus children would have learned by watching adults and older children, gradually developing the skills they would need as adults. They would have learned which plants were edible and which were poisonous, where to find water during dry seasons, how to track animals, how to make tools, and countless other pieces of practical knowledge. This intergenerational transmission of knowledge is one of the key features that distinguishes human societies from those of other primates and represents a crucial step toward the fully cultural beings that later human species would become. Plant foods such as fleshy leaves, fruits, nuts, roots, and tubers must also have been significant in their diet. Collections of hackberry seeds, for instance, were discovered in the Zhoukoudian cave deposits in China, where the renowned Peking man Homo erectus remains were found. The Zhoukoudian site, located about 50 kilometers southwest of Beijing, is one of the most important Paleolithic sites in the world. Excavations there, which began in the 1920s, have yielded fossils from more than 40 individual Homo erectus, making it one of the richest sources of information about this species. The cave deposits at Zhoukoudian are incredibly deep, in some places over 40 meters thick, representing hundreds of thousands of years of accumulated sediment, bones, tools, and other materials. The lower layers contain the oldest evidence of Homo erectus occupation dating to around 700,000 years ago, while the upper layers are more recent, around 200,000 years old. This means that Homo erectus occupied this site, perhaps not continuously but repeatedly, for 500,000 years. That's an almost incomprehensible span of time, during which countless generations of Homo erectus were born, lived and died in and around this cave. The hackberry seeds found at the site are particularly interesting because they show up in large concentrations in certain layers, suggesting they were deliberately collected and brought to the cave, probably in the autumn when they would have been ripe. Hackberries are small fruits that are high in carbohydrates and would have provided valuable calories. The fact that Homo erectus was collecting and consuming plant foods in large quantities reminds us that despite their reputation as hunters, they were actually omnivores who relied on a diverse diet. In fact, plant foods probably provided the majority of their calories, with meat serving as a valuable but perhaps not daily supplement. There appears to be little uncertainty that Homo erectus was omnivorous, an opportunistic eating approach that provided maximum adaptability. Modern humans are the most opportunistic of all living primates, and Homo erectus was probably one of the earliest human species to acquire this quality, granting the species with flexibility and evolutionary versatility. This dietary flexibility would have been crucial to their success. Unlike specialized feeders who depend on particular food sources and are vulnerable if those sources disappear, omnivores can adapt to changing circumstances, switching their diet as necessary to take advantage of whatever foods are available. This flexibility would have allowed Homo erectus to survive and thrive across the diverse environments they inhabited. From the tropical forests of Java to the temperate woodlands of China to the savannas of Africa. Though Homo erectus were capable hunters for their time, they would have also certainly been prey for fierce predators that occupied their environments. 2/3 of Homo erectus remains discovered in Longform, China, displayed damage compatible with that produced by carnivore teeth, most probably those of hyenas. One well-fossilized crushed Homo erectus skull discovered at Longform has puncture marks perfectly corresponding the teeth of the vanished giant hyena Pachecruta brevirostris, or short-faced hyena. Another cave in Juqian, China held skeletal components of Homo erectus individuals dispersed over sections of the cave floor up to 9 meters in diameter. Examination revealed that 67% of these Homo erectus remains displayed bite marks or other alterations attributed to large mammalian carnivores. Homo erectus probably experienced severe competition and continuous alertness due to the existence of dangerous predators, prompting an increased state of wariness and apprehension. Their capacity to create groups and work together for defense would have been a vital benefit. But for some unfortunate individuals, they would have certainly ended up as meals for ancient predators. What tools did Homo erectus utilize? They began with simple but productive hand axes for hunting and processing animals. But later in their evolutionary chronology, these hand axes became progressively refined, signifying substantial enhancements in their tool innovation and displaying the mental progress these early humans achieved. The earliest hand axes connected with Homo erectus are tools of the type discovered in Olduvai Gorge, Tanzania, where they were found in substantial quantities. These older tools were distinguished by their simple fabrication, mainly using core forms. These cores were river pebbles or comparable rocks that had been struck by a spherical hammerstone to produce conchoidal fractures, eliminating flakes from one surface to produce an edge and frequently a sharp tip. The dull end of these tools is designated the proximal surface and the sharp end is the distal surface. Older one is a percussion innovation grasping the proximal surface. The hominid would bring the distal surface down forcefully on an object they wish to separate or fragment, such as a bone or tuber. Skip ahead a couple 100,000 years in Homo erectus tool-making development, and you get more intricate hand axes designated Aculean, named after the location of Saint Acule in France. These tools emerged around 1.76 million years ago. Aculean tools were distinguished not by a core, but by a biface, a stone tool worked on both sides. The most remarkable form was the hand axe. The earliest Aculean axes emerged in the West Turkana region of Kenya and around the identical time in southern Africa. Aculean axes are bigger, heavier, and possess sharp, cutting edges that are chipped from opposite sides into a teardrop configuration. In opposition to an older one tool, which is the outcome of a fortunate and likely spontaneous operation to acquire one sharp edge on a stone, an Aculean tool is the planned outcome of a refined manufacturing procedure. The manufacturer starts with a blank, either a bigger stone or a slab knocked off a bigger rock. From this blank, the maker eliminates large flakes to be utilized as cores. Standing a core on edge on an anvil stone, the maker strikes the visible edge with centripetal blows of a hard hammer to approximately shape the implement. Then the piece must be worked over again or retouched with a soft hammer of wood or bone to generate a tool finely chipped all over, consisting of two convex surfaces meeting in a sharp edge. These more intricate Aculean hand axes persisted for more than 1 million years, with minimal alteration from the earliest versions, showing their productivity and proposing there was no requirement for enhancement. Though fossil remains of the tool makers themselves aren't always maintained alongside the tools, these hand axes clearly document the development of innovation, workmanship, acquired intelligence, and social conduct in a pre-human human community over a million-year period. Homo erectus manufactured other tools as well. Evidence displays they fashioned implements from shells at locations in Sangiran and Trinil spherical stones measuring 6 to 12 centimeters and 2.4 to 4.7 centimeters in diameter are regularly discovered in African and Chinese lower Paleolithic locations, and these were potentially utilized as bolus, throwing weapons consisting of weights linked by cords used to entangle prey. Beyond tools, did Homo erectus build shelters? Evidence indicates they did construct structures for defense. There are signs that Homo erectus built branch huts up to 50 feet long for shelter, occasionally with stone slabs or animal skins for floors. The first houses were believed to be simple windbreaks made of animal skins extended over a frame. The oldest identified shelter from this era was discovered at the location of Terra Amata near Nice, France in 1960. The shelter was a collection of 12 individual oval structures that spanned from 26 feet all the way to 49 feet in length, with widths between 13 and 20 feet. Homo erectus utilized fire to keep warm, and the huts within these shelters were surrounded with small rocks to form a fire line around the perimeter of dug pits for wood. Another outstanding location was found near present-day Bilzingsleben in eastern Germany, where ancient humans believed to be Homo erectus, though some contend they may have been Homo heidelbergensis, inhabited around 350,000 years ago. They built shelters comparable to those of Bushmen in southern Africa, circular structures with bone and stone foundations between 9 and 13 feet across. In the middle of each circle, archaeologists discovered an elephant tusk, which they theorized might have functioned as a center post. These findings point to a species with far more intricate behavior than previously envisioned, one capable of altering their environment to produce protected living spaces using fire for warmth and defense, and arranging their living areas in ways that indicate social structure and collaboration. In the next segment, we'll investigate one of the most revolutionary technologies mastered by Homo erectus, fire, and how this breakthrough fundamentally transformed the trajectory of human evolution. One of the most revolutionary dimensions of Homo erectus culture was their control of fire. The regulated use of fire essentially transformed human evolution, permitting our ancestors to keep predators away, prolong their waking hours beyond dusk, cook their food, and ultimately settle colder territories of the planet. Being able to generate and sustain fire meant that Homo erectus obtained unprecedented mastery over their environment and diet in ways no previous species had accomplished. Cooking food was especially transformative. Cooked meat is not only safer with fewer disease-causing organisms, but it's also far simpler to digest. The procedure of cooking breaks down rigid fibers in meat and plant foods, permitting more productive nutrient extraction with less digestive exertion. This may have contributed to the decrease in gut size that we observe in the Homo erectus fossil record relative to earlier hominins, potentially liberating energy for brain advancement, but precisely when our ancestors first controlled fire remains one of paleoanthropology's most heated controversies. Why? Because campfires very infrequently preserve well over extended periods of time, let alone for hundreds of thousands or millions of years. Despite these preservation obstacles, Homo erectus is extensively credited as the first human ancestor to have utilized fire, though the exact timing remains disputed. The earliest asserted fire locations include Kubi Fora in Kenya, dating to roughly 1.5 million years ago, and Wonderwerk Cave in South Africa, with evidence proposing controlled fire use as early as 1.7 million years ago. However, these early dates remain debatable among investigators, with some contending the evidence isn't definitive. The first Homo erectus firekeepers are believed to have simply carried and sustained naturally happening fires for prolonged periods rather than producing fire themselves. They might have opportunistically gathered fire from lightning strikes or natural brush fires, then carefully sustained it for as long as feasible. This would necessitate knowledge of slow-burning materials like dung that could maintain flames for prolonged periods. Interestingly, fire becomes noticeably more plentiful in the broader archaeological record after 400,000 to 300,000 years ago. This considerable increase could show either some progression in fire-making methods or perhaps propose that our human ancestors only opportunistically utilized fire until this time when they finally perfected dependable fire-starting techniques. It's completely possible that fire-starting innovation was invented, lost, reinvented, and independently found multiple times by separate Homo erectus communities rather than being invented in one place and distributing throughout their range. The obstacles of maintaining fire-making tools in the archaeological record make this difficult to establish with certainty. The earliest definitive evidence of hearths intentionally built fire pits comes from Gesher Benot Yaakov in Israel, dating to over 700,000 years ago. What makes this location especially compelling is that fire is documented in multiple archaeological layers in an area close to water, both traits that would be uncharacteristic of natural wildfires, powerfully proposing intentional controlled use. The advent of controlled fire use had deep social consequences as well. The long history of people sitting around campfires sharing stories probably started with Homo erectus, and this practice would have had a massive effect on the development of social abilities and possibly the intricacy of human communication systems. Collected around the safety and warmth of a fire in the evening, early humans would have had new possibilities for social attachment, knowledge distribution, and collective strategizing. Some investigators have suggested that increased social activity around campfires enabled the requirement for more intricate ideas to be communicated, potentially driving the advancement of more refined language abilities. The firelight would have prolonged waking hours into the night, producing time for social activities beyond mere survival tasks, perhaps the start of culture as we comprehend it. Beyond these technological and social progressions, archaeological evidence uncovers darker dimensions of Homo erectus society that force us to reevaluate our views of these ancient humans. Multiple Homo erectus skulls discovered in India display a substantial number of head wounds. Were these produced by warfare between groups, by hunting mishaps, by rivalry within groups? It's challenging to say with certainty, but they indicate violence was present in Homo erectus society. Even more provocatively, some archaeological locations hold human bones with cut marks comparable to those made with Homo erectus tools on butchered animals. These have been discovered in locations ranging from South Africa to Croatia, leading some scientists to theorize that cannibalism may have been part of Homo erectus behavior for hundreds of thousands of years. This wouldn't be completely surprising from an evolutionary viewpoint. Evidence indicates that even Homo sapiens participated in cannibalistic practices in the not-so-distant past. In Guff's Cave in the United Kingdom, anthropologists found bite marks on 15,000-year-old human bones that seem to display intentional consumption. The marks indicate the ancient consumers were attempting to scrape off every millimeter of nutritious muscle. Investigators also discovered hundreds of filing marks and ritualistic incisions on bones, and even uncovered skulls seemingly altered for use as cups. Similarly, Homo erectus skulls, dated to be 500,000 years old, discovered in caves at Zhoukoudian in China, seem to have been separated from the body and maintained presumably as trophies. Some investigators theorize the purpose may have been ritualistic, perhaps to symbolically acquire the strength or qualities of the deceased. However, critics of these assertions propose the marks on the skulls might have been made by giant hyenas rather than other hominins. Could Homo erectus speak? This question touches on one of the most vital transitions in human evolution, the advancement of language. Some scientists have hypothesized that Homo erectus must have had some form of basic language because they required to communicate to coordinate hunts and transfer information about tool making. However, the parts of the Homo erectus brain connected with reasoning, symbolism, and imagination seem to have been comparatively underdeveloped relative to modern humans. The frontal lobe, where intricate thinking occurs in modern humans, was relatively small in Homo erectus. Additionally, the spinal cord canal in Homo erectus vertebrae was more narrow than in modern humans, indicating limited nerve pathways between the brain and the muscles, regulating breathing and vocalization. Many investigators think Homo erectus didn't have the FOXP2 gene, frequently designated the language gene, in its modern form. This gene, which performs a vital role in the neural advancement necessary for language and speech, is discovered in its current form only in modern humans and Neanderthals. Based on these anatomical limitations, many scientists believe Homo erectus probably communicated with simple vocalizations, gestures, and facial expressions rather than intricate language with grammar and syntax. They may have utilized a limited vocabulary of distinct sounds to transmit basic information about food sources, dangers, or social status. Yet even in this basic form, the communication among Homo erectus would have represented a considerable advance beyond previous hominid species. The knowledge demanded to craft Achillean stone tools, for instance, would have been challenging to transmit without some form of demonstrative communication combined with vocal instruction. If we think of language abilities on a spectrum, with modern human language being the most intricate, Homo erectus might represent a vital intermediate stage not yet capable of the abstract and symbolic communication we take for granted, but far more refined than anything that had come before. In essence, if modern humans represent the apex of language development, equivalent to today's sophisticated technology, then Homo erectus might be compared to the Model T Ford of language, basic by our measures but transformative for its time and laying vital foundations for what would come next. Did Homo erectus produce art? Until not long ago, the earliest evidence of geometric art was dated from 70,000 to 100,000 years ago. Scratched patterns discovered in South African caves produced by early Homo sapiens. These engravings have been understood as signs of behavioral modernity, our species' distinctive cognitive journey into a refined world of abstraction and symbolism, but an extraordinary finding has pushed the origins of art back much further, potentially to Homo erectus. A zigzag pattern discovered on a fossilized shell from Java, Indonesia, has been dated to roughly 430,000 years ago, making it potentially the world's earliest documented engraving and showing that Homo erectus had both the manual precision and possibly the symbolic thinking required for artistic expression. The pattern consists of a zigzag line with 3 sharp turns generating an M configuration, a set of more superficial parallel lines, and another zigzag with 2 turns generating a sideways V configuration. A study performed by marine biologist Josephine Jordans and her colleagues determined that the morphology of the zigzags, internal morphology of the grooves, and differential roughness of the surrounding shell area shows that the grooves were intentionally engraved and predate shell burial and weathering. Other potential evidence of Homo erectus artistic expression encompasses the Middle Pleistocene Venus of Tantan and Venus of Barakat Ram, objects theorized to have been altered by Homo erectus to resemble human forms. These items were mostly shaped by natural weathering, but seem to have been slightly altered to emphasize certain grooves indicating hairlines, limbs, and eyes. The former has traces of pigments on the front side, possibly showing it was intentionally coloured. Homo erectus was also the earliest human species documented to have deliberately gathered red-coloured pigments, specifically ochre. This behaviour is documented as early as the Middle Pleistocene, with ochre lumps at Olduvai Gorge, Tanzania, connected with the 1.4 million-year-old Olduvai hominid 9, and at Ambrona, Spain, which dates to 424 to 374,000 years ago. In both locations, the ochre seems to have been struck by a hammerstone and deliberately shaped and trimmed at Terra Amata in France, which dates to 425 to 325,000 years ago. Red, yellow, and brown ochres were recovered in connection with pole structures. The ochre was likely heated to accomplish such a broad colour range. Since it's unclear if Homo erectus could have utilised ochre for any functional application, these discoveries might show that Homo erectus was the earliest human species to have displayed a sense of aesthetics and to think beyond simple survival requirements. One of the most astonishing capabilities attributed to Homo erectus is seafaring. Peculiar artifacts found on isolated islands that were never linked to mainland areas during the Pleistocene may display seafaring by Homo erectus as early as 1 million years ago. In Indonesia, they had reached the islands of Flores, Timor, and Roti, which would have required crossing the Lombok Strait, also designated Wallace's Line, at least before 800,000 years ago. This crossing wouldn't have been simple. The Lombok Strait is 24 miles wide, 250 meters deep, and has a fierce current due to its location as a main channel for the Indonesian through flow, the maritime link between two of the world's great oceans, the Indian and the Pacific. These oceans have distinctions in temperature and sea levels, producing treacherous water conditions. If Homo erectus genuinely did cross this strait, it indicates they possess the capability to construct refined watercraft and navigate dangerous waters, a degree of technological accomplishment far surpassing what was previously attributed to them. This would also powerfully show sophisticated communication capacities. If they could coordinate to paddle to remote islands, they must have possessed some form of spoken language to plan and execute such demanding voyages. Archaeological evidence also indicates Homo erectus may have engaged in forms of healthcare and social support. The earliest likely example of community care for sick or injured individuals is a 1.77 million-year-old Homo erectus specimen from Georgia who had lost all but one tooth due to age or gum disease, the earliest example of severe chewing impairment in the fossil record. Yet this individual lived for several years afterward. Unable to chew fibrous foods, they likely relied on soft plant or animal foods, possibly with assistance from other group members. Another persuasive case is a 1.5 million-year-old juvenile specimen called the Turkana boy, who was identified with juvenile spinal disc herniation. Because this individual was still developing, the condition produced some scoliosis. These conditions usually produce recurrent lower back pain and sciatica, pain running down the leg, and probably restricted activities like walking, bending, and other daily movements. The reality that this young person lived into adolescence despite these limitations indicates some form of community care and support. A 1 million to 700,000 year old Javanese specimen presents a noticeable osteophyte bone spur on the femur, probably resulting from Paget's disease of bone and osteopetrosis, abnormal bone thickening. These conditions likely resulted from skeletal fluorosis produced by ingestion of food contaminated by fluorine-filled volcanic ash, as the specimen was discovered in ash-filled strata. This individual would have had considerable difficulty walking and collecting food, representing a net negative to their group in purely survival terms. Yet they lived for years with these injuries, again offering evidence of sophisticated group care. For perspective, livestock that grazes on volcanic ash-ridden fields usually dies of acute fluorine intoxication within days or weeks. The survival of this Homo erectus individual with comparable exposure indicates intentional care from others in their group. These cases of apparent healthcare in Homo erectus populations uncover something profound about their social structure. Rather than abandoning sick or injured members who could no longer contribute fully to group survival, as might be anticipated in a society focused solely on immediate survival requirements. Homo erectus groups seem to have supported their vulnerable members, permitting them to survive despite serious health obstacles. This indicates levels of compassion, social attachment, and perhaps even a basic understanding of caregiving that goes far beyond the stereotypical caveman image of early humans. It shows that some of our most deeply held human values, caring for the sick and vulnerable, may have origins extending back nearly 2 million years, long before our own species appeared. What ultimately occurred to Homo erectus? After flourishing for nearly 2 million years, an almost unthinkable span of time relative to our own species' brief existence, Homo erectus ultimately vanished from the fossil record. But the question of why they went extinct remains a subject of ongoing investigation and discussion. The extinction was probably due to multiple factors, but the primary hypothesis centers on a combination of climate change and rivalry from later, more sophisticated human species such as Homo heidelbergensis, Neanderthals, Denisovans, and ultimately modern humans. A team of investigators found that Homo erectus lost a considerable portion of their habitable climate niche just before they vanished from the fossil record. This critical insight helps clarify their ultimate extinction after such a remarkably long reign. Species generally flourish when they have large, interconnected areas at their disposal, but when livable territories shrink and fragment into small, geographically isolated patches, species enter what ecologists designate an extinction vortex, a downward spiral toward disappearance. The extinction vortex is a terrifying concept in conservation biology. When a species' habitat becomes fragmented, populations become isolated from each other. Small, isolated populations are vulnerable to numerous threats. Inbreeding becomes more common, reducing genetic diversity and making the population less able to adapt to changing conditions. Random events like disease outbreaks or natural disasters can wipe out entire local populations. Without gene flow between populations, beneficial mutations can't spread, and harmful mutations can accumulate. Local extinctions become more frequent, further reducing the total population and accelerating the decline toward total extinction. For Homo erectus, this process appears to have been triggered by dramatic climate changes during the Pleistocene. These reductions in habitable area resulted from sudden climatic alterations. The research team discovered that Homo erectus went extinct during the last glacial period, which started roughly 115,000 years ago, probably the coldest climate conditions the species had ever encountered throughout their long evolutionary history. The last glacial period, sometimes called the last ice age, was a time of dramatic environmental change. Ice sheets expanded from the poles, covering much of northern Europe, Asia, and North America. Sea levels dropped by over 100 meters as water became locked up in ice, exposing land bridges between continents and islands. Global temperatures plummeted, rainfall patterns shifted, ecosystems that had been stable for thousands of years transformed rapidly, with forests giving way to grasslands or tundra, and grasslands becoming deserts. For a species like Homo erectus, adapted to the relatively warm conditions of the early and middle Pleistocene, these changes would have been catastrophic. The habitats they depended on shrank dramatically or disappeared entirely. The animals they hunted migrated to new areas or went extinct. The plants they gathered failed to thrive in the new, colder conditions. Water sources dried up or froze. Simply surviving from day to day would have become increasingly difficult. Unlike later human species like Neanderthals, who acquired specialized biological and cultural modifications for extreme cold, Homo erectus seems to have lacked the cognitive adaptability and technological innovations required to survive such substantial environmental shifts. Their tool innovation remained comparatively unchanged for hundreds of thousands of years, indicating a certain conservatism in their approach to environmental obstacles. This conservatism is actually one of the most puzzling aspects of Homo erectus. For a species that survived for 2 million years and spread across 3 continents, adapting to diverse environments ranging from tropical jungles to temperate woodlands, they showed remarkably little innovation in their technology. The Acheulean hand axe, which first appeared around 1.76 million years ago, remained essentially unchanged for over 1 million years. While there were regional variations and gradual refinements, the basic form remained the same across vast stretches of time and space. Why didn't Homo erectus innovate more? It's not that they lacked the cognitive capacity. Their brains were large, and evidence from tool-making, hunting strategies, and social behaviors shows they were capable of sophisticated planning and problem-solving. Some researchers have suggested that their very success may have worked against innovation. If Acheulean tools worked well enough for their purposes, if their hunting strategies were successful enough to keep them fed, if their social structures were effective enough to maintain group cohesion, then there would have been little selective pressure to change. The adage, "if it isn't broken, don't fix it," may have applied to Homo erectus technology and culture. But when environmental conditions change dramatically, this conservatism may have become a fatal flaw. Later human species, particularly Homo sapiens, showed much greater behavioral flexibility and technological innovation. When faced with new environments or changing conditions, they could rapidly develop new tools, new hunting strategies, new social arrangements. This flexibility allowed them to colonize virtually every environment on Earth, from Arctic tundra to tropical rainforests to deserts to high mountains. Homo erectus, despite their long success, simply couldn't keep up when the climate shifted rapidly and newer, more innovative human species expanded into their territories. The final stronghold of Homo erectus was on the island of Java in Indonesia, where they continued after vanishing elsewhere. This prolonged survival in Java can be clarified by the island's unique geography and climate. Being closer to the equator, Java encountered less substantial temperature fluctuations during glacial periods. Additionally, its isolation defended these final Homo erectus populations from rivalry with more sophisticated human species that were spreading across mainland Asia. Java provided a refugium, a place where conditions remained suitable even as they deteriorated elsewhere. The island's tropical climate meant that even during glacial periods, temperatures remained relatively warm and rainfall remained sufficient to support diverse ecosystems. The surrounding ocean provided a barrier that kept out competing human species, at least for a time. For tens of thousands of years after Homo erectus had vanished from mainland Asia, they persisted on Java, perhaps unaware that they were the last of their kind. But even this last refuge ultimately became uninhabitable for them. As the climate shifted, Java's environment transformed from the open woodland habitat connected with Homo erectus to expanding rainforest. These dense forests would have presented completely different obstacles for hunting, collecting, and movement. Obstacles that Homo erectus, with their comparatively static technology and behavioral patterns, may have been unable to overcome. Tropical rainforests are challenging environments for humans. The dense canopy blocks out sunlight, limiting the growth of understory plants and making plant food scarce at ground level. Most of the forest's productivity is concentrated high in the canopy, out of reach for terrestrial hunters and gatherers. The animals that do live at ground level tend to be small, scattered, and difficult to hunt. The constant heat and humidity promote rapid decay, making it difficult to preserve food or materials. Many rainforest plants contain toxins or are otherwise inedible without extensive processing. Modern hunter-gatherers who live in rainforests typically have sophisticated knowledge of plant processing techniques, tools specialized for rainforest hunting like blowguns and bows, and complex trade networks with groups in other environments to obtain resources not available in the forest. Homo erectus, with their relatively simple Acheulean technology and their apparent preference for more open environments, would have struggled to adapt to dense rainforest. As the forests expanded and their preferred woodland habitats shrank, the last Homo erectus populations would have found themselves squeezed into smaller and smaller areas, until finally they disappeared entirely, marking the end of humanity's most successful species. One debatable study even proposed that laziness and conservative tendencies contributed to their demise. Investigators pointed to locations in the Sunda region of Indonesia where Homo erectus utilized local low-quality stone for tools rather than traveling slightly further to acquire better materials that would have generated more effective implements. This apparent reluctance to innovate or exert additional effort for improved outcomes might have become maladaptive as environmental conditions transformed. However, this interpretation has been criticized by many paleoanthropologists as imposing modern value judgments on ancient hominins who operated within completely different constraints and pressures. It's vital to recognize that the concept of extinction might not be the most precise way to describe what occurred to Homo erectus. Many investigators now believe that Homo erectus didn't simply die off, but instead developed into new species of hominins like Homo heidelbergensis in some territories. This evolution probably involved interbreeding with other hominin species as they came into contact, producing complex patterns of genetic exchange that are only now starting to be comprehended through ancient DNA examination. the story of Homo erectus raises profound questions about human evolution and the nature of species boundaries. Rather than viewing human evolution as a linear progression from one species to the next, the evidence progressively indicates a complex, branching bush of diverse hominins who sometimes coexisted, competed, and interbred. Homo erectus represents not a failed experiment or an evolutionary dead end, but rather a vital foundation upon which later human diversity would construct. One intriguing aspect of Homo erectus that we haven't yet investigated is their apparent flexibility to extreme elevations. Recent findings indicate that Homo erectus managed to colonize high-altitude environments much earlier than previously believed. Archaeological evidence from the Tibetan Plateau shows that hominins were inhabiting at elevations above 4,000 meters as early as 1.6 million years ago, a time when Homo erectus was the predominant hominin species in East Asia. Inhabiting at such high altitudes presents serious physiological obstacles. Modern humans who aren't adapted to high elevations encounter hypoxia, oxygen deficiency, which can produce altitude sickness, diminished physical capacity, and even life-threatening conditions like pulmonary or cerebral edema. The reality that Homo erectus evidently managed to survive in these environments indicates they may have acquired biological modifications to cope with reduced oxygen levels, modifications that may have later been transferred down to modern high-altitude populations through interbreeding or shared ancestry. This high-altitude colonization shows yet another way in which Homo erectus proved remarkably flexible, pushing into environments that would have seemed forbidding to earlier hominin species. From seaside environments to mountains, from tropical forests to open savannas, Homo erectus managed to flourish across an astonishing array of habitats, a flexibility that foreshadowed the global spread of later human species. Another area of ongoing investigation concerns Homo erectus's relationship with water beyond the evidence for possible seafaring mentioned earlier. Some investigators have suggested what's designated as the aquatic ape hypothesis to clarify certain Homo erectus traits. This debatable theory indicates that some human characteristics, including our relative hairlessness, subcutaneous fat distribution, and voluntary breath control, might have developed during a phase when our ancestors spent considerable time in shallow water environments, perhaps wading, swimming, and foraging for marine resources. While mainstream paleoanthropology has largely dismissed the strongest versions of this hypothesis, there is growing evidence that coastal and riverine resources performed an important role in Homo erectus. Subsistence approaches, archaeological locations along ancient shorelines display evidence of shellfish consumption, fish processing, and other aquatic resource utilization dating back hundreds of thousands of years. The capacity to exploit these abundant food sources high in proteins and omega-3 fatty acids that support brain advancement may have offered vital nutritional benefits. Some investigators theorize that access to these brain-boosting nutrients might have contributed to the encephalization increasing brain size that characterizes Homo erectus evolution. We focused extensively on Homo erectus biology and technology, but what about their potential emotional and social lives? While we can never understand with certainty the inner experiences of extinct species, the archaeological evidence offers some tantalizing clues. The care for injured and disabled individuals mentioned earlier indicates social bonds that transcended mere survival utility. The reality that Homo erectus groups supported members who could no longer fully contribute to subsistence activities shows emotional attachments and perhaps even concepts of reciprocal care that extended beyond immediate family units. Some locations also propose possible ritual behaviors. The arrangement of stone tools and animal remains at certain Homo erectus locations displays patterns that seem intentional rather than purely functional. While we should be cautious about projecting modern human symbolic thinking onto ancient species, these patterns hint at the beginnings of ritualized behaviors that might have reinforced group identity and social cohesion. The possible collection and alteration of objects without obvious utilitarian purpose, like the ochre pigments and potentially symbolic items mentioned earlier, further indicates that Homo erectus may have had the cognitive foundations for aesthetic appreciation and perhaps even basic symbolic thought. These capacities, while probably much less developed than in modern humans, would represent a vital step toward the abundant symbolic and cultural worlds that characterize later human species. An intriguing area of speculation concerns how Homo erectus might have comprehended their world. Without intricate language or writing, their conceptual frameworks would have been primarily rooted in direct experience rather than abstract categorization. Their knowledge would have been deeply embedded in specific landscapes passed down through demonstration and imitation rather than explicit instruction. Some cognitive archaeologists propose that Homo erectus may have had what's designated mimetic culture, the capacity to represent knowledge through intentional bodily movements like gesture, dance, and non-linguistic vocalization. This form of communication, more refined than that of great apes, but less intricate than fully syntactic language, would have permitted them to share information about tool-making methods, hunting approaches, and environmental knowledge. This mimetic capacity might clarify how Homo erectus managed to maintain comparatively consistent tool-making traditions across vast geographic areas and time periods without written instructions or intricate verbal explanations. The stability of their technological traditions over hundreds of thousands of years indicates effective systems for knowledge transmission that relied primarily on observation and imitation. The social structure of Homo erectus groups remains speculative, but some clues come from comparisons with both great apes and modern hunter-gatherers, as well as from the archaeological record itself. The sexual dimorphism in Homo erectus, while less pronounced than in great apes, indicates males were somewhat bigger than females, which might show social structures with some degree of male dominance or rivalry. However, the collaborative hunting approaches evidenced at locations like Olorgesailie in Kenya propose coordination between multiple individuals, a degree of collaboration that usually requires comparatively egalitarian social relations. The most probable scenario is that Homo erectus inhabited small, adaptable bands with fluid membership, comparable to, but perhaps less intricate than those of modern hunter-gatherers. Within these groups, knowledge about resources, territories, and methods would have been shared through direct demonstration and accumulated through experience. Elders might have held particular value as repositories of environmental knowledge, knowing where to locate water during droughts, which plants were edible in different seasons, or how to predict animal migrations based on subtle environmental cues. As we piece together the Homo erectus story from fragmentary fossil and archaeological evidence, one thing becomes progressively evident. These were not simple, primitive creatures barely removed from their ape ancestors. They were intricate beings with extraordinary modifications, social lives, and cognitive capacities that permitted them to flourish across vast spans of time and space. Their legacy lives on not just in the fossil record, but potentially in our own genomes and behaviours. Recent genetic investigations have identified archaic hominin DNA in modern human populations that doesn't match documented Neanderthal or Denisovan signatures. Some investigators theorize this genetic material might represent Homo erectus contributions to our genome through interbreeding events that happened before our species fully diverged from other hominin lineages. If validated, this would mean that Homo erectus lives on not just as an ancestor species, but as a direct genetic contributor to modern human diversity. Even more profound is the cultural and technological legacy of Homo erectus. Many of the fundamental technologies and modifications that define humanity, from controlled use of fire to the crafting of refined stone tools, from expanded geographic range to collaborative hunting, first appeared or were considerably developed during the long reign of Homo erectus. In a very real sense, they laid the groundwork for all that would follow in human evolution. As we reflect on the extraordinary journey of Homo erectus across 2 million years of Earth's history, spanning 3 continents and countless environmental alterations, we gain perspective on our own species' brief existence. Modern Homo sapiens have existed for only about 300,000 years, roughly 15% of Homo erectus's tenure. Our global civilization with its cities, agriculture, and digital technology represents less than 1% of that time span. The long success of Homo erectus reminds us that evolutionary success isn't measured by technological intricacy or cultural refinement alone, but by flexibility and resilience across changing conditions. By this measure, Homo erectus ranks among the most accomplished mammals, not just hominins, to ever walk the earth. Their story also challenges us to reconsider what we mean by human. The traditional narrative of human evolution frequently portrays a linear progression from primitive to sophisticated, with each new species representing an enhancement on what came before. But the emerging picture from paleoanthropology proposes something far more intricate and interesting, a diverse family tree of human species, each with unique modifications and capabilities, sometimes competing and sometimes interbreeding, all part of the abundant tapestry of human evolution. Homo erectus wasn't a failed experiment or an imperfect draft of humanity. They were an extraordinarily accomplished species in their own right, with modifications perfectly suited to their time and place in evolutionary history. The reality that they ultimately gave way to other human species, including our own, doesn't diminish their extraordinary achievement in pioneering so many of the traits and technologies we now consider fundamentally human. In a world where our own species faces unprecedented environmental obstacles from climate change to resource depletion, the story of Homo erectus provides both inspiration and caution. Their extraordinary flexibility permitted them to flourish across diverse environments for an almost unthinkable span of time. But ultimately, even they could not overcome the combined obstacles of rapid climate change and rivalry from more technologically sophisticated species. As we contemplate the legacy of Homo erectus, perhaps their most profound contribution to human evolution wasn't any specific technology or modification, but rather their pioneering of a new ecological niche, what anthropologists designate the human adaptive niche. This unique position in Earth's ecosystem involves using cultural and technological innovations to buffer against environmental obstacles rather than relying solely on biological modifications that usually take thousands of generations to develop. Homo erectus was the first species to substantially expand this distinctly human approach to survival. While earlier hominins displayed glimmers of cultural modification, Homo erectus took this approach to unprecedented levels, crafting diverse tools, controlling fire, expanding into demanding environments, and acquiring social systems that permitted knowledge to accumulate and spread across generations. This shift fundamentally altered the trajectory of human evolution. Natural selection started operating not just on physical traits, but progressively on cognitive and social capabilities that enhanced cultural innovation and transmission. The result was a feedback loop between biological and cultural evolution that would ultimately produce our own species with its unprecedented capacity for symbolic thought, intricate language, and technological innovation. Recent excavations at locations in Ethiopia have revealed evidence that challenges traditional views of Homo erectus capabilities. Stone tools discovered at Gona display a degree of craftsmanship previously believed beyond their capacities. The precisely shaped implements reveal careful selection of raw materials and refined knapping methods that demanded not just manual precision, but also sophisticated planning and spatial reasoning. What's especially striking about these discoveries is their age. Dating to roughly 1.6 million years ago, they display that Homo erectus accomplished this degree of technological refinement much earlier than previously believed. This pushes back the timeline for sophisticated cognition in human evolution and proposes that the mental capabilities of Homo erectus have been systematically underestimated. The geographical distribution of these sophisticated tools also tells us something significant about Homo erectus societies. Comparable technological traditions have been discovered across widely separated territories, proposing some form of cultural transmission mechanism that permitted innovations to spread between separate Homo erectus groups. This hints at social networks and intergroup contact that would have enabled not just technological sharing, but potentially also mate exchange, resource information, and other vital survival knowledge. Another overlooked dimension of Homo erectus life involves their relationship with other species beyond hunting and avoiding predators. There's emerging evidence that Homo erectus may have participated in forms of proto-domestication, the beginnings of the intricate relationships between humans and other species that would later transform into full domestication. At several Homo erectus locations, archaeologists have discovered unusual concentrations of certain animal species that don't match natural accumulation patterns. These concentrations might represent the earliest evidence of humans producing ecological niches that attracted particular animals, perhaps by clearing areas of vegetation or producing water features that drew specific prey species. While this falls far short of the intentional breeding programs that characterize genuine domestication, it represents the first steps toward the human manipulation of other species' evolutionary trajectories, a procedure that would ultimately transform wolves into dogs, wild grains into crops, and reshape Earth's biosphere in countless ways. The cognitive implications of such environmental manipulation are considerable. It proposes that Homo erectus had some understanding of cause and effect over extended timeframes, recognizing that altering the landscape in specific ways would attract certain animals, potentially making hunting more predictable and productive. This capacity for environmental engineering represents yet another way in which Homo erectus transcended earlier hominin species. Rather than simply adapting to their environment, they started the distinctly human practice of adapting environments to suit their requirements, an approach that would reach its apotheosis in modern human civilization, but has its roots in the behavior of these ancient pioneers. The question of consciousness in Homo erectus remains one of the most captivating and elusive dimensions of their existence. While we can never directly access the subjective experience of an extinct species, the archaeological record offers tantalizing clues about their mental world. The degree of planning evident in their more refined tools proposes they had what psychologists designate autonoetic consciousness, the capacity to mentally project oneself into the future and plan accordingly. This capacity for mental time travel represents a vital cognitive leap beyond the primarily present-oriented consciousness of most non-human animals. Similarly, their care for injured group members shows some form of empathy and perhaps even theory of mind, the capacity to recognize that others have mental states separate from one's own. The long-term care evidenced by healed injuries in some fossils, propose they could comprehend the suffering of others and were motivated to alleviate it, cognitive and emotional capacities that we usually associate with sophisticated consciousness. Even more intriguing are the hints of aesthetic sensitivity and potentially symbolic thought in their collection of colourful materials and possible artistic productions. These behaviours propose that Homo erectus may have encountered subjective states beyond mere survival calculation, perhaps even the beginnings of aesthetic appreciation, curiosity, and wonder that characterize the human consciousness we understand today. While their mental world was certainly different from our own, lacking the scaffolding of intricate language and accumulated cultural knowledge that shapes modern human consciousness, it would be a mistake to view Homo erectus as merely instinct-driven automatons. The archaeological evidence paints a picture of beings with abundant subjective experiences, social bonds, accumulated knowledge, and perhaps even the beginnings of symbolic thought as we continue to unearth new evidence and acquire more refined analytical methods. Our understanding of Homo erectus continues to develop. Recent methodological innovations have permitted investigators to extract new types of information from long-studied fossils, revolutionizing our picture of these ancient humans. Sophisticated imaging methods like micro-CT scanning have revealed internal bone structures that offer insights into growth patterns, diet, and health conditions, not visible from external examination alone. Isotope examination of teeth has opened windows into seasonal migration patterns and dietary alterations throughout individual lifespans. Ancient protein examination has started to complement DNA investigations, providing molecular evidence from specimens too old for genetic material to survive. These methodological progressions have transformed Homo erectus from a comparatively static, one-dimensional species in the textbooks to a dynamic, diverse, and intricate branch of the human family tree. We now recognize considerable regional variations, evolutionary alterations over time, and nuanced modifications to separate environments that paint a far more refined picture than earlier generations of investigators could access. Looking forward, emerging technologies promise to further revolutionize our comprehension. Enhancements in ancient DNA recovery methods may ultimately permit genetic material to be extracted from Homo erectus fossils despite their age and frequently challenging preservation conditions. This would offer unprecedented insights into their evolutionary relationships, potential interbreeding with other hominin species, and genetic modifications to separate environments. Meanwhile, agent-based modeling and other computational approaches permit investigators to test hypotheses about Homo erectus, social structures, movement patterns, and ecological relationships that couldn't be directly tested through archaeological evidence alone. These approaches, combining traditional archaeology with cutting-edge technology and computational techniques, represent the future of paleoanthropology. What lessons can we draw from the Homo erectus story that might inform our understanding of our own species' future? Perhaps the most sobering is that even extraordinary evolutionary success doesn't guarantee indefinite survival. After flourishing for 2 million years, a time span that dwarfs our own species' existence, Homo erectus ultimately vanished, unable to adapt to the combined pressures of climate change and rivalry. This provides a powerful reminder of vulnerability even for highly flexible species. Our own global civilization faces unprecedented obstacles from climate change, resource depletion, and biodiversity loss. The fossil record reminds us that no species, no matter how accomplished, is guaranteed continued existence when environmental conditions transform dramatically. Yet the Homo erectus story also provides hope. Their extraordinary flexibility permitted them to pioneer survival approaches that ultimately led to our own species. They showed the power of cultural innovation, social collaboration, and technological advancement to overcome environmental obstacles. The very approaches that might assist us navigate the obstacles of our own time. The key distinction is the time frame of alteration. Homo erectus encountered environmental shifts that unfolded over thousands of years, permitting time for cultural and biological modification. Today's anthropogenic climate change is happening at a pace unprecedented in human evolutionary history, compressing into decades alterations that would normally take millennia. This compression demands a degree of foresight, global collaboration, and technological innovation beyond anything our evolutionary history has prepared us for. Yet, the seeds of these capacities were planted by Homo erectus when they first expanded the human adaptive niche to encompass cultural and technological buffers against environmental alteration. In this sense, we owe our potential for overcoming today's obstacles to innovations pioneered by these ancient relatives almost 2 million years ago. Their legacy lives on not just in our physiology and possibly our genomes, but in the distinctly human approach of using cultural and technological innovation to transcend biological limitations. As we close this investigation of Homo erectus, we return to the extraordinary time span of their existence. For roughly 2 million years, a period so vast it challenges our comprehension, these beings walked the earth. They witnessed countless generations, ice ages, changing landscapes, and the rise and fall of innumerable animal species. They spread across 3 continents, adapted to environments from tropical forests to high-altitude plateaus, and pioneered technologies that transformed the human evolutionary trajectory. Their story isn't a footnote in human evolution or a primitive prelude to our own species. It represents the most accomplished chapter in human evolutionary history, a testament to the extraordinary flexibility, resilience, and innovativeness of our ancient relatives. In studying Homo erectus, we gain perspective not just on human origins, but on what it means to be successfully human in evolutionary terms. The genuine legacy of Homo erectus isn't just in the fossils and artifacts they left behind, but in the fundamental human capacities they pioneered: technological innovation, social collaboration, environmental flexibility, and the cultural transmission of knowledge. These capacities, refined and elaborated through subsequent human evolution, remain at the core of what defines humanity today. So the next time you control fire to cook a meal, utilize a tool to solve a problem, adapt your behavior to a changing environment, or share knowledge with others, remember that you're drawing on capacities pioneered by Homo erectus almost 2 million years ago. Their evolutionary innovations echo through time, connecting us to our ancient past and shaping our ongoing human journey into the future.